Hi, thank you for your interest in this topic. So this presentation is recorded for Bernoulli One World Symposium and is based on the joint work with Jorge Gonzalez Cazares. So I would like to consider a Levy process on a finite time interval, so say 0, 1. So Levy process is a process with stationary and independent increments and can be always decomposed into the Brownian part and the rest. So the jump part plus possibly linear drift. So what I have here is a non-negative constant sigma, W is a standard Brownian motion, and Y is an independent Levy process with no Brownian part. As is usual in applications, we assume we don't have full knowledge of the trajectory of X. Rather, we have observations on a regular grid. So we have X at times I over N, where I runs from 1 to N, from 0 to N. So we have N increments of the Levy process X only. Now, as N goes to infinity, one can study various statistics and various quantities, and there is rich asymptotic theory underlying that. Here I cite just a few papers, but I could have put here many more. So one very basic example is that sigma can be consistently estimated, so the standard deviation of the Brownian component, and it can be estimated with the rate square root n. The question I want to consider here is quite different from the mainstream theory. So I would like to know if it's possible to recover the Brownian part and the jump part from high frequency observations of the Levy process X. So given this skeleton of X, can we get W and Y as N goes to infinity? So one of the main applications in mind we have is, in fact, in many practical applications of Levy processes, Y is quite often interpreted as the signal and W is the noise. So we aim to separate signal from the noise, right? Of course, this is a very basic decomposition. So one would also like to know if we can actually decompose from the high frequency data. So there are other applications, but let's not go further into that. So one immediate problem on this way is that it is impossible to separate linear drift from a Brownian path consistently due to Girsanov's theorem, change of measure argument. But apart from that, this program is feasible, and in fact, we have two approaches discussed in the paper. You'll find the link to the paper preprint in the very last slide. But here, also in the paper, we focus on the first approach, which is firstly quite surprising. I hope you will find that as well in a few minutes. And secondly, it doesn't have any tuning parameters. So it's very easy to implement, and it seems it works, right? So let me discuss the surprising part. I would like to consider, first of all, just a Brownian motion, just standard Brownian motion, or rather it's skeleton. So we have the random walk, we have the grid with 1,000 points, right? So this is actually how you would simulate Brownian motion. You just simulate 1,000 increments. This is one trajectory, and independently we simulate another gray trajectory. Now what I want to do is I find the order of the red increments, so the ranks of the red increments. So which one is the smallest, largest, and so on and so forth. And then I just reorder the gray increments accordingly and sum them up. So consider the partial sum again. So, and what I get is the following thing. I get the blue trajectory, and I hope you are very surprised at this point. You see it's actually very similar to the red one, even though it's these are independently sampled normal increments, just the order is matched with the order of the red one. So of course, there is different linear slope. So let's bring the endpoints to 0. So we look at the Brownian bridges, well, the skeletons of those, and indeed they look very similar. So there is something here. Now I take the same Brownian path. I simulate independent 1.2 stable process in green. And then I just sum it up with the red one to get the yellow Levy process. And this yellow Levy process, well, the yellow skeleton is the only thing which is available to us, right? So now what I do, I simulate independent normal increments. I reorder them according to the yellow increments. I get the partial sums. And this is how it looks like when we look at the Brownian bridges, right? When we bring the endpoint to 0. So again, you see a very close similarity, but now, of course, the rate of convergence is slower. Right, so the main result is the following. For the Levy process X observed on a dense grid, we assume that sigma is known. It's positive, well, it can also be estimated. We construct the skeleton W by reordering independent normal increments according to the order of X. Note, it's just 2 lines in R to implement that, right? And then we have this recovery result. So the approximating bridge over here converges to the true bridge. But since we know the skeleton of X, we can also recover Y. Well, we have the joint recovery up to a random independent linear drift over here. Convergence is in supremum norm as n goes to infinity, well, in probability and in supremum norm. And recall from Gersanov's theorem that we can't actually do better than this. In fact, we have a stronger result, which also states the rates of convergence. But for the sake of this talk, I decided to simplify and assume regular variation on the Levy measure. So the rate of jumps exceeding x is assumed to be of a power form. So x minus alpha times some slowly varying function. You can take it here as a constant. It's what you would get in the stable case. And alpha is necessarily in between 0 and 2. Right, so when alpha is 0, you have essentially very simple processes like compound Poisson and so on. And then the rate is essentially n to the power 2 minus alpha over 4, the rate of recovery. So when alpha is 0, you have essentially square root here. And in this case, the process y is very different from Brownian motion on small scale. But when alpha increases, the process y becomes closer and closer on small scale to Brownian motion, and then the rate deteriorates. The exact statement is here. So for p larger than alpha, we look at this uniform error multiplied by this term, and then we have convergence in probability to 0. And this convergence fails for any p below alpha. When alpha is 2, we don't have prefactor here, and we say that the recovery indeed works, and the rate is slower than any positive power in this case. This result is in fact much more general because of the change of measure argument once again. So for example, W can be a Bessel process or something like that. Let me discuss quickly numerics. So here we take alpha stable process for different alpha from 0.2 to almost 2, right, when the rate should be really bad. And now we, I think, replicate the error. We compute this error for the bridges, uniform error, and we replicate that 100 times. And these are the mean errors here denoted by the circles for different n, and on the log-log scale, right? And then the slope predicted by the previous result is, we draw the lines according to that slope, minus 2 minus alpha divided by 4, and anchor that line at the midpoint over here. So you see the predicted decay, the predicted rate matches the actual rate as it should. Well, we have much more in the paper, so you're very welcome to consult that. There is exact rate and the limit for a piecewise linear Y. So for these simple processes, it doesn't need to be a Levy process. We can go much further, but otherwise things become very complicated. Also, we have the case of no Brownian component, and we show that in that case, even though we couple with X, the new increments, the result is asymptotically independent. So these things can be used, for example, for testing for the Brownian component. Finally, there are proofs, the reasons. We try to also single out the reasons of this phenomena, and we also discuss possible extensions. Finally, there is an alternative approach based on threshold filters, and you're very welcome to consult the paper by following this red link. Thank you very much for your attention.